Welcome! In this video I'm going to build this DC electronic load. It's powered by a Raspberry Pi. It has a vacuum fluorescent display. It's good to about 100 watts. Anyway, I'm going to start with the design of it, and then I'm going to show some of the circuit boards and such that I created, and then we're going to do a demo of it. I'm going to start with the basic DC load circuit. This is a circuit that I've been using variants of it ever since watching a video on EEV blog years ago. I built several manual DC loads, a few computer controlled ones. So I'm going to start with the most basic circuit, which is this here. And basically what we have here is a current sense resistor. Label that. Now a 1 ohm resistor, if you pass 1 amp through it, that will generate 1 volt. So 1 amp at 1 ohm equals 1 volt. So that is how we can use this resistor to sense how much current is going through this path. If you pass half an amp through it, you'll get half a volt, etc. And that forms sort of the basis of the circuit. So what we're going to do is we're going to make use of that measuring on that current sense resistor to run it over here to one side of an op amp. On the other side of an op amp, we're going to basically feed it with a potentiometer. The potentiometer will vary between 0 and some number of volts. In this case, I've got a 9 volt regulator, so it varies between 0 and 9 volts. This op amp gate here is just a unity gain. Whatever goes in comes back out. So we take our 0 to 9 volt signal there. So this op amp will continuously compare the value coming from this current sense resistor with the value coming from this set point. If the current sense is less than the set point, then it will start to turn on the op amp's output. If the current sense is greater than the set point, then it will start to turn off the op amp's output. And on the output of our op amp, we're going to come over here and we're going to drive the gate of a big power MOSFET. So if the current sense is below the set point, the MOSFET turns on and starts pulling current down through this path. Basically this way. That will cause more current to go through the resistor, which will cause a higher voltage. Our feedback will come here. Eventually we'll get to the point where our feedback is equal to our set point. We'll reach an equilibrium state, and our current sense voltage will be equal to our set point. We will be providing the amount of amps that we desire to have set. So that's the basic circuit. I've added a couple parts here, this capacitor and this resistor. What I found is these two are necessary to dampen the oscillations of this circuit. If I didn't have these in there, I get some horrible oscillation feeding the gate to this MOSFET, and rather than get a steady current following the set point, we would have it oscillate by as much as 5 amps up and down from the set point. So these dampening components were certainly necessary there. This down here is just a regulator, nothing to see there. So this is a basic DC load that you can build pretty much out of parts from your junk box. All you really need is an op amp, a reasonably beefy current sense resistor, any decent power MOSFET, and a potentiometer, and you've got yourself a manual DC load. So what we're going to do is we're going to go from this manual version to a computer controlled version. So I've made a few changes here, but I'm going to show you how they're all really the same as the circuit we just had. So first of all, this current sense resistor, I moved it off board. You can see it's here, it's an external resistor, it's got a couple wires on each end of it going to some terminal blocks. The reason I did that is so I can use a great big huge metal encased 50 watt power resistor for that won't overheat. So the same resistor, just wired in a little bit differently. We've got the same op amp. This side is unity gain, this side is doing the comparison and driving the gate. You can see I've added some additional components in here. Resistor mark 0 means just jumper it. One mark no populate means don't populate it. So those are just in so that I could do some experimentation with the circuit. This jumper here, you just jump it across. And then the MOSFETs, you'll see there's now 3 of them. The reason I did that is you don't want to overheat those. So if you put 3 of them, you can kind of get them to load share between the 3. It's not perfect. There'll still be a little bit of thermal difference between them, but it beats having a single MOSFET. So what you're seeing is 3 MOSFETs in parallel. I added resistors to the gate drives on them. They're all tied together, all hooked to the output of the op amp. So basically we've got the same circuit, op amps, current sense resistor, MOSFETs. Now over here, rather than drive it with a potentiometer, we'll drive it with a D-to-A converter. I chose the MCP 4821. It's nice 8-pin through-hole integrated circuit. It requires no external voltage reference, pretty easy to use. I also built my board so that I could use 4921s. You'll see I've got some parts down here I've X'd out. Those are all an external voltage reference for the 4921, but you just use the 4821 and jumper this across. So a D-to-A converter hooks to a microcontroller. It's got its digital interface here, a chip select, a serial clock, and a serial data. Hook that to the Raspberry Pi. And based on the value you send to it digitally, it'll output a voltage between, I believe in this case, 0 and 4 volts. This is a 12-bit D-to-A converter, so it will have 2048 steps. So that is our control path for operating this thing. Raspberry Pi somewhere, D-to-A converter, our op-amp circuit, our current sense resistor, and our MOSFETs. I've added a few more things on here. So there's this little 4-pin header that's for sensing. There is an amp sense. The amp sense simply hooks up to one end of the current sense resistor. So by reading that with an A to D converter, you can see how much amps are actually flowing through that resistor. There's a V sense, which is voltage sense. It goes from here over to here, and there's a voltage divider comprised of a 75K resistor and a 1K resistor. And what that does is that takes the voltage that's coming in from the load, and it reduces it down by a significant amount, so it will be within about a 4 or 5 volt threshold. There's also a Zener here for protection, just in case we somehow got a surge. We don't want to send out more than 5 volts out our sense pin and damage whatever's sensing. So down here on the sense, we will have an ADS1115. We will hook it up to 1 pin to the amp sense, 1 pin to the volt sense, and 1 pin to ground. So we've got A, got V, and ground. So the ADS1115 I2C, so the ADS1115 is an analog to digital converter. It will read the voltages on these 3 pins and send those to our Raspberry Pi. So this gives us a way to get feedback on how our circuit is behaving. So even though we've commanded a certain thing here, you would like to know that what's happening across the current sense resistor is what you actually asked for. And we can tell both amps and we can tell voltage. And the ADS1115 will run it on a little daughter board. I didn't build it into the DC load board itself. Okay, here is the DC load's main circuit board. So we've got 2 ICs. We have this one here is the D-to-A converter. This one here is the op-amp. Back here we've got 3 MOSFETs. They're all hooked to a common sink. Now the back of these MOSFETs is live and is connected to the source voltage. So it is necessary to isolate this heatsink from a case. If your DC load was, you had it hooked up to 100 volts or something, this heatsink here may be at 100 volts. So for that reason, I decided that I would isolate this. It's not going to have any screws going from this directly out into a place where a person might touch. It's going to be surrounded by a plastic case, etc. Here's a connector for the resistors and stuff. So I ended up using these pluggable headers. So this here is the actual connector for the jacks going to the front panel. They'll just plug in there like that. These headers are real nice that you can plug them in like that. The headers themselves, I believe, came from Amazon, real cheap. This base here, the vertical base, I think is a leftover one from DigiKey. What else is there to see on this? Well, here, this is an interesting thing. I designed this board to have a 7805 regulator, but it gets really hot powering a Raspberry Pi. So I ended up using this Easy SBC drop-in switching replacement for the 7805. I've used these in other projects before. This Easy SBC board, it's relatively cheap, and it's a great way to eliminate one of those hot regulators like 7805 with a nice efficient switcher, so I put that in. You've got some headers for connecting to the Raspberry Pi there and there. Yeah, some of the resistors are optional, so they're not populated or they're jumpered across. I don't think there's a whole lot more to see. There's a power jack here. It's powered either by the power jack or via this 2-pin header adjacent to it. The bottom of the board is pretty normal. Now, if you look at other loads, they have just an absolute huge heatsink. So one of the things I wanted to do with this project is to see could I succeed with a smaller heatsink. So this is a relatively small heatsink, and we will get to measuring this performance in a little bit, but I think we'll find that this is just fine for my design goal of ballpark of 100 watts or so. Hi, this is the front panel that I designed. I've used similar front panels in my other projects. It's kind of a refinement of the panel. Often I've tried to make the panel fit the same size as a Raspberry Pi 4 hat, but that's really kind of confining, so I decided to go a little bit bigger than a Raspberry Pi. So it's, maybe, half an inch to an inch taller and half an inch wider or so. You can see I have mounted a Pi Zero W on the back. On the front, we have a vacuum fluorescent display. Noritake makes those. You could also use one of these common, $5 LCDs if you want to. I vastly prefer the vacuum fluorescent display. I've got 3 buttons on each side here. Each button has a surface mount LED in front of it, so that I can make kind of these plastic extensions to go through the case. This is made out of clear PETG, and you can actually see the light pass up through the button, so we can have kind of illuminated buttons. In the middle I have the SparkFun RGB encoder. It's got 3 LEDs in it, a red, a green, and a blue, and you can make any color combination out of controlling those individual LEDs. It's got a good detent, and it is pushy, so you can push on it. Up here we have a potentiometer. In case you're using LCD, you need to set contrast. If you're using the VFD, you don't have to set contrast with a potentiometer. On the back, we've got the Pi Zero W. I used to use Raspberry Pi 3s and 4s in my projects, but you really don't need anything more than the Zero W. And the Zero W is a lot smaller and more convenient. We've got an MCP 23107 I/O expander that runs the encoder, it runs the display, it runs a lot of stuff on here to free up some of the Pi's address lines. I've got a socket here where I could plug in a D to A converter if I wanted, and I have a header that mounts these daughter boards for the ADS, ADS 1115 4-channel A to D converter. Now you might ask why I didn't just solder the A to D converter to my own circuit board where I use this daughter board. And the reason is simple. I've been able to get these daughter boards really cheap, like under $1 each from eBay. It prevents me from having to do that surface mount soldering on this board. And I think I can get the daughter boards cheaper than I could buy the chip. We've got a couple headers here. There's some redundancy in these headers. For example, I've broken out the I2C pins 3 different times so you can plug in 3 different things. The SPI pins are there, the analog to digital and the digital to analog, some GPIOs, all comes out there. We've got a transistor that could be used to drive a relay or a fan or something like that. And we just plug this back into there, and that's complete. So this new front panel board has been working out for me pretty well in this project, and you'll see it demonstrated when we go to try out the completed project. Okay, the DC load is all hooked up and ready to try out. It's all kind of precariously balanced here, so I hope you can see everything. I hope I'm not going to knock anything over while I'm trying it out. Here is the processor board with the LCD encoders, the analog to digital converter, the Raspberry Pi Zero W. It's all sandwiched together here. Connects via a cable to the DC load board with its 3 MOSFETs, a heatsink. Over here is the 0.1 ohm resistor. We have a 12 volt Noctua fan back here. Kind of taped a piece of plastic on to simulate how I expect the case is going to work once I put this thing in a custom case. I'm going to kind of blow lengthwise down the fan. I'll have some vent holes over at this side. Kind of the idea that the air can flow across it like that. I've got my Fluke hooked up here to measure the amperage. And I have my benchtop supply delivering 24 volts. So let's try this out and see how this thing works. I suspect it's going to need some tuning. First of all, you can see I've got a cursor. Hope you can see the cursor. It's right there. I can switch which digit I want this on all the way up to the amps position down here to the milliamps position. That's the set point. Next we'll read the actual amperage via the analog to digital converter, the actual voltage, and the power. Power being voltage times amperage multiplied together. So the first thing to notice is that there's a little bit of weirdness here. The actual is measured at 0.028 amps, even though we've got the set point at 0. And the problem that we've got there, and I think I could correct this with a simple subtraction, is the offset voltage of the op amp. The op amp has an offset voltage of about 2.8 millivolts, so whatever signal we put into the op amp reads 2.8 millivolts higher. Because we're measuring everything through that 0.1 ohm resistor, that's getting multiplied by 10, and that's giving us 28 milliamps of offset. So when we said 0, we've got 28. So it's always 28 milliamps ahead, and there's no way to kind of remove that 28 milliamps. No matter how high we adjust this, it's still going to be stuck in there. I am going to explore in a revision coming up with a way to apply an offset to the op amp to compensate for its built-in offset, and we'll see if we can get that out of there. But for right now, let's assume this thing has a minimum amperage of 28 milliamps. You just can't go beneath that. The voltage is also reading a little bit off. I assume that is just lack of precision in the resistor network I'm using. We'll just have to tune this voltage. We could tune it in software and it would read accurately. So the voltage going into this really is 24 volts and it's reading about half a volt low. So, okay, and the actual 28 milliamps there is actually read over here. About a similar reading on the Fluke. There may be a little bit of difference between what the Fluke says and what the A to D converter says, because we don't know that this resistor here is dead on. This resistor does have a 1% tolerance. It could be off by as much as 1%. So anyway, let's try ramping this up a little bit. Well, I've also got my thermal camera here, so we can look at our temperatures. Right now, all of our MOSFETs are at 22 Celsius, all 3 of them. So let's bring this up to about an amp. So again, that offset is still in there. We set our set point to 1 amp. We're still getting that 2.8 millivolts of offset on the op amp, so we're still reading about 28 milliamps higher than we wanted. The voltage has gone down a little bit due to drops in the cable, and we're computing the power at about 24 watts. Got a little bit of drift between what the Fluke says and what the ADC is saying. And again, I think that may be due to tolerance in that resistor. We'll have to see if we can trim that out in software. We should be starting to generate some heat back here. Oh yeah. Our MOSFETs are 30 Celsius, 32 Celsius, and 31 Celsius. So I would like to let it sit for about 5 minutes and just see if it warms up. So I'm going to... Okay, I've given it about 5 minutes. Let's see what our temperatures are up to. We're up to about 40 Celsius, about 44, and about 42. Let's crank it up. Let's crank it up to 100 watts. So maybe 4 point something will get us there. There, 102 watts. That's 4.5 amps. Let's let it sit here for 5 minutes and see how the heat is doing. Okay, let's take a reading. Now we're up to 108 on the first MOSFET, 122 on the second, 120 on the third. So the temperature limit, according to datasheet on these MOSFETs, is 150. So let's see if we can go a little bit higher. Let's just stop at 125 watts. Okay, it's been going a while. Let's take some readings. The first MOSFET, I'm reading 131. The middle one, I'm reading 186. That's well beyond what the datasheet says is tolerable. And the third one, I'm reading 183. So clearly 125 watts is too much. Okay, here is the front panel assembled. So I have printed this plastic piece on my 3D printer. This is in atomic filament marble PETG. You can see the displays in the middle. We've got our 6 buttons, our encoder, and some jacks here to connect the load to the source that it's going to be applying a load to. There's also room for a power switch. I have one more spot for another jack that I was going to use as a pick-off to hook up an oscilloscope to be able to monitor how the load was performing, whether it's oscillating. I'm not sure whether I'm going to do that. I may just plug that if I don't use it. If I do, I'll put another jack there. It mounts via 4 screws. You can see the back is kind of set up like this. You've got posts for the 4 screws, and you've got some channels here where the buttons fit inside of. And then each button is kind of a long rectangle that sits in that channel. Okay, so here I have put everything into my 3D printed case. This is printed out of PETG. This is Overture PETG on the outside, and atomic filament marble PETG for the front panel. We've got the main board for the DC load with its heatsink back there. We have a Noctua 60mm fan here, exhausting the air. I did test it. It is much better to exhaust the air than to blow the air in. We have the load resistor mounted to the side. We have the front panel components here. We actually have down here a Dallas DS18B20 temperature sensor mounted to the heatsink, so we can measure how hot the heatsink is getting. The lid goes on here with thread certs. So put it on like so. Gonna flip it on its end. So I'm gonna hook the thing up and run it up to 100 watts, and we will see how the cooling works out in the case. Okay, there, it's reached a steady point at about 77 degrees Celsius at about 100 watts. There is a lot of heat coming out the side vent. It's blowing a lot of hot air out of there, but it is steady and stable. So I would say it has met the design parameters that I had in mind of 100 watts. without overheating or melting the case.
Okay, given that the whole goal of this was to make it Raspberry Pi controlled, let me show off the web UI. So it's a Raspberry Pi, it's a 0W, so it has built-in wireless Ethernet, and I have written a web application in Django, my favorite web application framework, that has a simple control panel. So here we will see a few buttons and knobs and status. So currently it's getting 0.28 amps and there's 23.447 volts, and it's computing the watts and it's showing you the temperature inside. Temperature's a little bit high because I've been playing with it and it's gotten a little warm inside. And then down here you've got the desired amps. So there's a slider for that. You can slide this back and forth to set the amps, as well as some buttons and an entry box. Right now you'll notice it's at 0.001 amps and we're getting 0.028 amps. We've still got that issue there with the 2.8 millivolt offset in the op amp, so it's still reading approximately 0.28 amps higher than it's supposed to. I still haven't trimmed that out or corrected that, but for now, just pretend they were equal. We can take our desired amps, we can slide it up. I mean, let me get it up somewhere around 1. There, 1.007. So we can see 1.007. It's still, off by that same amount that I plan on fixing. And you can see, the volts has come down a little bit due to cable loss. The watts is being computed. And the temperature there is at 34.1 Celsius. We can use these buttons to quickly change things. I can increase by a milliamp, 10 milliamps, 100 milliamps. I can increase by an amp, or I can decrease. Everything adjusts as appropriately. If you want to set a value, just set it to 1 amp. Set it to 4.325 amps. Easy enough. And if I wanted to, I could put some graphing in this. I could have it export to Prometheus and Grafana if I wanted to for data logging. Now that this thing is on a Pi and web enabled, there's just all kinds of different things I can do with it. Let me ramp this back down. There's still a few things that I have left to do on this. The most important to me is to get rid of this offset voltage that's going between the set point and the op amp. I'm either going to correct that in hardware or in software. To do it in software, it's just going to simply be, add 0.028 to this number when you print it, easy enough. Doing it in hardware would be better because I think this offset voltage is somewhat dependent on temperature, and it may not be always 0.027 amps or 0.028. It's a little bit fuzzy, so best to try to find a hardware solution to that. If not, I'll do a software solution. The other thing is I need to do is to measure all of the resistors and make sure that we know the known resistance. A bunch of them are 1%, so they could be off by as much as 1%. So that's the current sense resistor as well as that voltage divider on the feedback voltage. So want to get all that stuff nice and accurate. So we'll do some adjustments there.
Okay, bonus material time. So I ordered myself some bigger heat sinks from Amazon. This bigger heat sink cost about $8. Here's the big one. Here's the original one that's been in the video so far. So you can see it's about half again as tall. It's about twice as deep. Same length. But it also, I think the fins look to be a lot thinner on this, and there are more fins and they're longer, so I think this is going to cool a lot better than the heatsink I've got in there. So let's take a look. And here is the case with the larger heatsink. So I'm not going to run all the way through this and power it up and demo it again with the bigger heatsink. But I did run some results off camera and record some temperatures. So the 100-watt temperature on this came down to 44.5 degrees Celsius. So that is actually nice and cool. The 125-watt came down to 50 degrees Celsius. And I even ran it all the way up to 200 watts. And 200 watts, we were sitting at 74.8 Celsius. Now 74.8 degrees Celsius, that is getting high, but it's still reasonable for this project. So I think I'm going to go ahead and I'm going to leave that bigger heatsink in there, and I'm going to call this a 200 watt load instead of a 100 watt load. Thank you for watching my video. Please visit my website at www.smbaker.com for more electronics projects and sandrail stuff. Bye.